Let's continue with different cases of applying phase conditions to find the RootLocus for the closed loop control. Okay, in this case, we're going to look at multiple poles. When you have multiple poles or zeros on the real axis for the open loop, the closed loop poles will have to move in different directions from that multiple pole. And we need to find out in what angle or in what direction they're going to move out. Okay, because they have to break off and they can't move together towards a single direction. So for example, the diagram here, I have one open loop pole at P1 point. I have one open loop 0 at Z1 point. I have R number of open loop poles over here. Now these poles will be the starting point of some of the closed loop poles, okay? But they will move in different directions. They're going to break it off for the closed loop poles as you increase the K. Open loop poles will stay there, but the closed poles will move in different directions. And we want to find out what these directions are. Okay, so to find this, I'm going to put a test point somewhere near that multiple pole position. Okay, I'm going to put somewhere there that's near it. And I'm going to find an angle between these multiple open loop pole to my test point. So I'm going to draw a line from there to that test point, which will give me an angle of theta, because when we apply phase condition, we are only concerned with angles rather than the magnitude. Magnitude comes later for gain condition. I'm going to draw a line from this open loop 0 towards that S0. This will give me an angle of theta 2. And also I'm going to draw a line from that point, P1, that's the open loop pole, towards my test point, and that will give me the angle of theta 1. So all the angles are between these lines and the positive real axis. Now for the phase conditions, which says all angles add together must equal to minus pi. The angles between this point and open loop zeros will be positive. The angles between this point and all the open loop poles will be negative. So that's really the phase condition we have. So I'm going to apply that. The angle between this point and this open loop 0 is theta 2. That's theta 2 positive. The angle between this point and this multiple pole is theta. But I have R number of them. So you have to multiply that by R. So that's R theta. Every single pole, open loop pole count once. So you have 5, you have to count 5 times. You have 3, you have to count 3 times if they're the same on the same point. Give me the same angle, but I need to count it 5 times, or R number of times in this case. Then I have theta 1 is the point between my test point and this open loop pole. So add all the angles together, because that will be a minus, okay? Add all the angles together, that must be a minus pi. Okay, this is just to give you integers of 360 degrees. So that's the condition I derived from the phase condition. Now imagine if I push this towards here, I'm pushing this down towards there, getting closer and closer to that multiple pole. Look at that angle. What happened to that angle? What happened to that angle? As I push this down, this line will moving towards the axis, this line moving towards the axis angle. This axis. Therefore, this angle becomes pi, this angle becomes pi. So when this is getting very, very close to it, we don't know this angle because it's the same line here, but we know this angle will be pi, this will be pi. Okay, so Substitute theta 2 by pi, substitute theta 1 by pi, so it's pi minus pi, they cancel each other out. Then we are left with r minus r theta equal to minus pi plus minus 2l pi, or r theta equals to pi plus minus 2l pi. Divide r to both sides, I get the angle, this angle, equals to pi over r. R is the number of multiple poles here, plus minus 2l pi over r. Okay. So I'm going to use an example here. I'm going to run an example here, which is very similar to this, what we have on in this general case. So in this example, I have s plus 2, which will give me an open loop 0 at minus 2. I have s plus 1 for the pole. That gives me a pole of minus 1. This is the pole. But I also have s plus 3 to the power of 4. So therefore, it gives me 4 additional open loop poles at minus 3. That's my P. So R is 4 over here. Okay, the rest is the exact same. So if I look at the angle, if I look at my test point, okay, I form an angle between the multiple pole, the 4 times P. This is my departing angle, theta. I'm looking at this angle between this test point and open loop 0 at minus 2. I'm looking at that angle between my test point and the open loop pole at minus 1. This will give me a pi. This will give me a pi as I move s naught towards there, towards the multiple pole. So minus pi cancel that pi out, I get this. Theta equals to 1 over 4 pi plus minus 2l pi. Now, from here, I need to work out the departing angles. Okay, because I have some variables here. I have the L I can change. Because I have 4 poles here, so they should move in 4 different directions. Okay, so I need to find 4 different angles. The way you do it is because L, we know L will be an integer number. You just try different integer numbers until you get 4 different answers. Okay, try any more, you will find a repeat of the same angles. So you won't find anything more than 4. So copy that down. Theta equals to 1 over 4 pi plus minus 2l pi. When L equals to 0, second term disappears. I get 1 over 4 times pi. That's pi over 4. That's 45 degrees. When L equals to 1, so this inside a bracket, it becomes pi plus minus 2l pi, or 2 pi. That's pi plus minus 2 pi. And that plus will give me 3 pi over 4. 3 pi over 4 is the same as, 3 pi over 4 or pi minus 2 pi. That gives me a minus pi and divide by 4. So I get 2 answers here. 3 pi over 4 or minus pi over 4. L equals to 2. So this becomes pi plus minus 2 times, so that's 4 pi. So 4 pi here. So I get 5 pi over 4 or minus 3 pi over 4. Now I need 4 differences. I get pi over 4, that's 45 degrees. I get minus pi over 4, that's my minus 45 degrees. I also get 3 pi over 4. That's just slightly less than pi, so that will be 135 degrees. And I also get minus 3 pi over 4. That will give me minus 135. Now you might say, well, what about this? This is actually the same. If you If you minus 2 pi to this, that's the same as minus 3 pi over 4. So it's the same answer you get there. We're not really getting anything additional. This is a repeat of the one of these. Or 2 pi. It's actually going around one more cycle. So I have 4 different angles. Therefore, this multiple pole will move, the 4 poles will move for the closed loop, not open loop. Okay, open loop poles stay there. The closed loop poles will move one towards 45 degrees, one towards minus 45 degrees, one towards 135 degrees, one towards minus 135 degrees. That is the case how we can actually work out. Okay, in this particular example, we have another open loop 0 and an open loop pole to consider. And this will give the answer. But if the transfer function doesn't give you all that, then it changes a lot. Okay, it doesn't have to be the 45, not because it's a multiple 4. It necessarily means that will be 45 degrees or minus 45 degrees, because if I change the transfer function slightly, I'm taking away that pole. Okay, in this example, I have this transfer function. If I take s plus 1 away to give me a different system, okay, if I have a different system, then the answers will be different. Okay, so in this case, I have a 1, 0 at minus 2 and 4 poles at minus 3. Now if I apply the phase condition, I get this theta times 4 and negative because it's pole. This theta 1 is positive, and when I push this towards there, that gives me pi. Okay? Or minus pi. It really doesn't matter. It won't change anything, pi or minus pi. Okay? Because you push there, you look at from positive side, you get positive pi. If you look at from negative side, you get a negative pi. So let's say it's a negative pi. Okay? Positive pi will give you the same answer. I can assure you. Okay? So it's negative pi minus 4 theta equals to minus pi plus minus 2l pi. That's my phase condition. I just lost 1 pi here because I lost open the pole for this particular example. Okay, because there is no pole, therefore there's no additional open the pole, therefore this becomes 0 here. So minus pi cancel that minus pi here, and then I'm going to divide 4 to both sides. I end up with 1 over 4 plus minus 2l pi. Now if I try different L values for this, L equals to 0, I'll get 0. L equals to 1, I'll get positive minus 2 pi divided by 4, and then I'll get positive half pi over 2 or negative pi over 2. L equals 2. L equals 2. 2 times 2 equals to 4. 4 divided by 4, that's 1. So I get plus minus pi. That's plus minus pi. Plus minus pi is the same. So L equals 1 give me a 0 degree. L equals 1 give me a 90 degree and a minus 90 degree. L equals 2 give me a minus 180 degree or minus 180 degree. So now, because there's no additional open loop pole, these 4 poles will break up in a different pattern. It's no longer 45 or 35. One will break up, moving along the real axis towards the positive side, one towards the left-hand side, one going vertically at 90 degrees, one going down vertically at minus 90 degrees. You can see all the poles for the open loop transfer function, all the zeros from open loop transfer function, they matter. The difference between these two examples is just that missing pole. Okay, in this example, I don't have that additional pole here, therefore they become 45 degrees. in this example, I have a pole here. You end up with 45 degrees. In this example, I don't have additional pole here. We end up with 0, 180, plus 90, and a minus 90. But in essence, what you need to do, because you don't always get the same transfer function or similar transfer function, in essence, you need to apply the phase condition. Work out the angles. If they are open loop zeros, then they are positive. If they are open poles, then they are negative. Add them together, then it should equal to minus pi. Okay? And then you work out the angle, the departing angle in relationship, and then apply different L values to give you different angles. Different system will end up with different solutions. That is an entirely different case. Case number 4. We're going to look at a system where the open loop system will have 2 real poles and 1 real zero. Now, if you identify the poles and zeros on the S-plane, you will find in this particular example, I have the open loop zero on the left-hand side of 2 open loop poles. So the example I give here only applies to that. Okay. Now, when that happens, if we look at the open loop 0 and 2 poles, and there's a pole here, there's a pole there, there's 0 there. That breaks the real axis into 4 different sections. We can actually examine which section is part of RootLocus, which section is not part of RootLocus, by just counting the number of open loop poles and zeros to the right, towards right-hand side. So between B and C, if you look at towards the right, there's only 1 pole. So this section is on RootLocus. Between section A and B, there are 2 poles towards the right-hand side, so this section is not. On the left-hand side of A, you have 1 0, 2 poles. Therefore, this section is on RootLocus. If you look at the right-hand side of C, any point here, look further towards the right, there are no open loop zeros, so therefore this side can't be. Again, closed loop poles will start from open loop poles, so these B and C will be the starting point for the closed loop poles to move. So as you increase K, this one, we made that argument before, it can't move towards the right, it can only towards the left. And this one can only moving towards the right. They meet each other. What will happen then is when they meet each other, they break off, they follow a circle. Okay? The center of that circle is that open loop 0. The center of that circle is that open loop 0. The radius is the geometrical mean between this 0 and this pole, and this 0 and this pole. Basically, what you're doing here is R, the radius of that circle, equals to square root the distance between A and B, and distance between A and C. So work out the distance here, work out the distance between A and C, multiply them together, square root, that will give you the radius. And so you follow that circle, one goes up, one goes down, and they meet up again on the real axis, on the other side of the circle. And then after that, if you increase the K even further, then one of the closed poles will move towards this open loop 0 along the real axis. The other one will move towards the left-hand side towards infinite along the real axis. Okay, because we know if you are given a transfer function, you will know A, B, C values. So first thing you need to check is if the open loop 0 sits on the left-hand side of the 2 open loop poles. If that is the case, then you follow that rule. If not, then you can't. Then you find the radius. You draw a circle with a center at open loop 0. And of course, because you know all the numbers then you can mark where this point is, where that point is. Okay, so that will form the complete RootLocus diagram. From there, they meet each other. One goes over, one goes down, and then one moves towards 0, the other one moves towards the left-hand side. Things change if they are not. If the open loop 0 is not on the left-hand side, okay, they don't follow this rule anymore. I got a couple of examples here. For example, now in the previous case, the open loop 0 is here. And we know this section is on RootLocus, and the pole has to move towards here, the pole has to move towards there. And when they meet each other, they have to break off. And then they're attracted by the quantum 0, so they're actually towards the 0 here. Now in this example, if I move the pole, if the open loop 0 is actually in between two closed loop open loop poles, then the rules would be different. In this case, if I count the number of poles and open loop poles and zeros to the right hand side of this section, I know there's only one. I know this section is on the RootLocus. This section is not. This section is on the RootLocus. Okay, and this section is not, because there are no open loop poles and zeros. So if you look at that pole, for the closed loop, as you increase k, there's nowhere else for it to go. You can only move in towards left, towards that open loop 0. For this pole, you can only move towards the left-hand side as well, because that's the only part of the real axis near the closed pole that's on the RootLocus. So you can move to there. So it's actually a lot simpler than the previous case. You will not get two poles meet each other and break off. Therefore, you can't have that circle. Similarly, if I have a case where open loop 0 is actually on the right-hand side of the two poles, again, this section is on RootLocus, this section is on RootLocus, so this pole will move towards this 0, this pole will move towards infinite. Again, because the middle section, the section between B and C, if you look at this section, look towards the right-hand side, there's one pole, 1, 0, 1 plus 1 equals 2. So this section is not on the RootLocus. Therefore, they can't move towards each other. Therefore, they can't meet, and therefore, they can't form a circle. Okay, so it is only when you have two open loop poles, one open loop 0, and open loop 0 is on the left-hand side of two open loop poles. That's when this scenario exists. Okay, and you can work out the distance between A and B, the distance between A and C, and work out the radians accordingly. So I'll give you an example here. I have a closed loop system, open loop system like that, where the transfer function is s plus 1, s minus 0.5, s plus 0.5. I want to draw the sketch. So sketch RootLocus diagram, and I also want to find the k value when the system becomes stable, and I want to find the k value when the closed pole is moved to minus 0.2 point. Okay, now if you look at the open loop, I have 1, 0 for the open loop equal to minus 1. I have a positive pole, 0.2, which means the system is unstable. I have a negative pole at minus 0.5. So if I identify them on the S-plane, this is one of the open loop pole, positive 0.2. This is the one of the open loop pole, minus 0.5. This is minus 1, that's open loop 0. So open loop 0 is actually sits on the left-hand side of the two open loop poles. Therefore, my scenario should be true. So I need to work out the radians first. Radians equal to square root the distance between this 0 and one of the poles, so that's 0.5. The distance between this pole, I think they probably, distance between this pole and 0.2 2 positive. So the distance is 1.2, not 0.7. Okay? And the answer is the same. It's a typo, okay? Answer will be 0.775, but it should be 0.5, which is the distance between this 0 and this pole. And then 1.2 is the distance between this and 0.2. Okay, so that should be 1.2. 1.2 times 0.5, that's 0.6. Square root should be 0.775. So therefore, this is the entire RootLocus diagram. This pole for the closed loop moving towards left, this pole moving towards the right, and then they follow the circle, and follow the circle there, they break off, one moving towards right, one moving towards left. Now I also need to identify where that is and where that is. But I know the center, I know the radius. So the center is here, the radius is 0.775. So this point, the point there must be minus 0.225. You can mark it here. This point is, this is minus 1. This distance is 0.775. So this point must be minus 1.775. So everything will be there. The arrows, okay? Don't forget to mark the arrows. That's the first part. That's the RootLocus diagram. But also I can work out the gains as well. To make the system stable is when this closed loop move from here to there, where s equal to 0. So all I need to do is work out the distance between s equal to 0 and 0.2, which gives me 0.2, between s equal to 0 and 0.5 or minus 0.5. Again, I want the distance, not the signs. Okay, so that's 0.5. The distance between this s equal to 0 and minus 1 is 1. Therefore, it's 0.2. 1, that's because it's 0, so you put them in the denominator. So 0.2 times 0.5 divided by 1, that'll give me 0.1. Then, if I want to work out the control gain to make the closed loop pole moving to minus 0.2. So minus 0.2 is somewhere there. Okay? Now, to do that, I need to work out the distance between this point and positive point 2. Minus 0.2, positive 0.2, that'll give me 0.4. Minus 0.2 to minus 0.5, that will give me a distance of 0.3. Okay? Minus 0.2 to the open loop 0, 0 minus 1, so the distance was 0.8. So that will be 0.4 times 0.3 over 0.8. That'll give me 0.15. So if I set again to 0.1, system will be marginally stable because this pole will move from there to there. But if I set again a bit more, it will move the pole to somewhere there. So the system becomes more stable and performance will be better. Okay, time for you guys to practice. Okay, again, I have some transfer functions here. I want to use, for some of them, I want you to find the departing angles. And for some of them, I want you to sketch the RootLocus diagram. There are different scenarios, and not all of them you can actually apply the conditions or copy my approaches. Okay, so but I actually pointed out different scenarios anyway, so you might as well just analyze where the poles are, analyze where the open loop zeros are, and then make a decision if any of the which scenario it actually fits into, and apply that scenario accordingly. Okay, thank you.